There is a machine running in your kitchen right now. It has been running, essentially unchanged in its core design, for nearly 200 years. Not upgraded, not redesigned. The same fundamental principle, operating on the same trapped gas, driven by the same mechanical pump, just with better insulation, and a digital thermostat bolted on top. The refrigerator is one of the most consequential inventions in human history. Remove it from American infrastructure for a single week, and the food supply chain collapses. Hospital pharmacies lose temperature-sensitive medications. Entire climate zones become functionally uninhabitable during summer. It is everywhere, it is invisible, and almost nobody thinks about how it works or how old the idea actually is. Here is what makes this story unusual. The country that invented the refrigerator may also be the country that ends it. Not with a better version of the same machine, with something so different that it has no moving gas, no chemical refrigerant, and makes almost no sound at all. And the key component is a piece of metal discovered accidentally by a Navy researcher trying to build a better missile nose cone, where the refrigerator actually comes from. Most people, if asked, would guess the refrigerator emerged from European industrial laboratories in the late 19th century. The actual origin is earlier and more American than that, in 1834. A man from Newburyport, Massachusetts, named Jacob Perkins patented the first working vapor compression cooling machine. Perkins demonstrated that a special gas, compressed mechanically and then allowed to expand, could extract heat from an enclosed space reliably, and on demand he could make ice. He could keep things cold in an era before electricity, before modern chemistry. Before industrial manufacturing, he built the core system that still hums behind you in your kitchen today. Nearly 2 centuries of engineering refinement have followed. Better materials, better refrigerants, better insulation, electronic controls, but the operating principle has not changed. Compress a gas, release heat, expand the gas, absorb heat, repeat indefinitely. That single loop, Perkins's loop, underpins every refrigerator, every air conditioner, every commercial freezer, every pharmaceutical cold storage unit currently operating in the developed world. The question worth asking is why nothing has replaced it. The answer is not that nobody tried. The answer is that every alternative approach encountered a specific engineering wall that nobody could get around for 50 years until a research team in Maryland tried pushing in a completely different direction. The problem with the machine you already have. Vapor compression refrigeration has 2 structural problems that have never been resolved, only managed. The first is mechanical. The compressor, the pump at the heart of every refrigerator, contains pistons that cycle continuously, thousands of times per hour, for the entire operational life of the appliance. That is the hum you hear from your kitchen at night. That hum is also a countdown. Moving parts wear, bearings degrade, seals eventually fail. The compressor is the reason refrigerators die. And it is the reason they make noise. The second problem is chemical, and it is significantly more serious at scale. The gases used as refrigerants are sealed inside the system, but sealed imperfectly. They seep at joints, they escape during maintenance, and they are released in large quantities when appliances are scrapped. Many of these gases carry global warming potentials that are difficult to communicate without the numbers feeling abstract. R134A, one of the most widely used refrigerants of the past generation, has a warming impact approximately 1,400 times greater than an equivalent mass of carbon dioxide. Now multiply one refrigerant leak by every refrigerator, every car air conditioning system, every commercial freezer, and every rooftop cooling unit operating across the country. The United States government has formally acknowledged this problem. The AIM Act, passed in 2020, committed the country to phasing down high-warming refrigerants by 85% over 15 years. The legislation exists, the timeline is in motion. The replacement chemistry, however, is not clean. Leading substitutes are either flammable, operate at higher pressures, or break down into compounds that regulators are already studying with concern. The country has legislated itself into a situation where the working fluid the entire cold chain depends on must be replaced, and no fully satisfactory replacement fluid currently exists. Which is exactly what pushed American researchers toward a different question entirely. What if the answer is not a better gas? What if the answer is no gas at all? The rubber band you already understand. Before the Maryland laboratory and before the Navy metallurgist, there is a physics demonstration you can do right now with materials in your home. Take a thick rubber band, stretch it quickly, and hold it against your upper lip immediately after. It will feel warm noticeably, so now let it relax completely and press it to your lip again. It will feel distinctly cool. You just ran a refrigeration cycle with your hands. What you felt is real physics. When you deform certain materials rapidly, you force their internal molecular structure into a more ordered arrangement. The transition to order releases heat. When the material is allowed to return to its relaxed state, the structure becomes disordered again, and that disorder absorbs heat, pulling it from whatever the material is in contact with. An English scientist named John Gough described this effect in 1805. James Joule quantified it decades later. It is called the Elastocaloric effect. The principle is not complicated. The problem was always practical. A rubber band degrades within weeks of continuous cycling. It cannot move meaningful quantities of heat, and no material existed that could survive the millions of deformation cycles that a real appliance demands until a Navy researcher accidentally created one while working on something entirely unrelated. Here is a question to carry into the next section. If this effect has been understood since 1805, why did it take until the 21st century to build a working machine around it? The answer involves a direction of force that nobody tried for 50 years, the metal with memory. In 1959, a metallurgist named William Bueller was working at the Naval Ordnance Laboratory in White Oak, Maryland, on a project with no connection to refrigeration. He was attempting to develop a better nose cone material for a Navy missile, mixing nickel and titanium alloys in search of useful mechanical properties. What he produced had properties that were genuinely unprecedented. The alloy could be bent significantly out of shape and would snap back elastically. More remarkably, it could be deformed at one temperature, cooled, and would then return to its original shape when reheated, as if the metal retained a memory of the geometry it wanted to occupy. The material was named Nitinol, from Nickel Titanium Naval Ordnance Laboratory. It is an American invention, funded by American military research, and it is now found inside cardiac stents in millions of patients, in eyeglass frames, and in aerospace actuators worldwide. But nitinol's most extraordinary property for cooling applications is its phase change behavior. When compressed, its crystal structure transitions into a tighter, more ordered phase, and it releases heat. Not by a fraction of a degree, but by tens of degrees. When released, it drops equally sharply and draws heat aggressively from its surroundings, a rubber band with aerospace-grade material properties. A solid-state refrigerant you can hold in your hand. The United States Department of Energy conducted a formal assessment of alternatives to vapor compression cooling and ranked elastocaloric technology, the application of nitinol type materials, to refrigeration at the top of the list of non-vapor compression technologies with genuine replacement potential. Not one of several promising candidates. First, so why was there no nitinol refrigerator in 2010? In 2015? The answer is a specific engineering failure that destroyed every prototype built for 5 decades, the wall that stopped every prototype. The obvious approach to building an elastocaloric cooling system is to stretch the nitinol to put it under tension, pull it, let it go, and harvest the cold. This works. It works well. And then it stops working because the material fails. Here is why. When you pull any metal under tension, every microscopic flaw in the material invisible voids grain boundaries. Surface irregularities becomes a stress concentration point. Each pull opens those flaws slightly. Each release allows them to close, but each successive cycle opens them marginally more than before. This is metal fatigue, and it is the same mechanism that allows you to snap a paperclip by bending it back and forth, even though you could never break it in a single pull. A kitchen refrigerator runs its cooling system continuously for 10 to 15 years. That is not thousands of cycles. That is tens of millions. Early elastocaloric prototypes were failing within weeks of continuous operation. Researchers would assemble a functioning device, begin testing, and watch the active component develop hairline fractures and shear apart. A second problem compounded the first. Nitinol requires substantial mechanical force to trigger its phase change. Generating that force requires significant energy input. Early prototypes were spending large amounts of energy to strain the material and recovering only a fraction of it as usable cooling. The efficiency numbers were not competitive with a compressor that had been optimized by global industry for a century and a half. By the 2010s, elastocaloric cooling had a consistent reputation in the engineering community. Beautiful underlying physics, broken practical execution, a technology that could demonstrate impressive cooling performance right up until the moment it destroyed itself. The Maryland team studying this problem understood the fatigue failure better than anyone else, largely because they had broken more nitinol than anyone else. And at some point in that work, they asked a question that sounds almost too simple. What if we stop pulling it, the direction nobody tried? The insight from the University of Maryland team. Working in collaboration with the Department of Energy's National Laboratory System under materials scientist Ichiro Takuchi, was fundamentally about mechanics. Cracks propagate under tension. Tension opens flaws, but compression does the opposite, it closes them. Squeeze a piece of metal rather than stretching it. And the microscopic voids that would normally grow into fractures are being clamped shut on every cycle rather than forced open. The team built their system around Nitinol tubes driven in compression, squeezed along their length by hydraulic force rather than pulled apart. The same phase change, the same heat release and absorption, but operating under conditions where the failure mechanism of tension-driven fatigue is replaced by the stabilizing effect of compressive stress. The results, published in the journal Science, demonstrated materials performance far beyond what elastocaloric devices had previously achieved, and into a range where the technology becomes a genuine competitor to vapor compression rather than a laboratory curiosity. The physical architecture that emerged from this work is worth understanding. A bundle of thin nitinol tubes is compressed hydraulically. As they compress, they heat, and a loop of water, plain water, with no chemical refrigerant properties and no environmental hazard, carries that heat away to external coils. When the driver releases, the tubes return toward their remembered shape, drop sharply in temperature, and the water loop returns to collect the cold and deliver it to the refrigerated space. Notice what that description does not contain. No refrigerant gas. No global warming potential of any kind. No chemical that regulators are working to phase out. The only fluid in the system is water. The only refrigerant is a solid piece of metal that never leaves the machine. If the entire system were to rupture in your kitchen, the consequence would be a water puddle. Notice also that a compressor must run continuously, because stopping it allows the gas pressure to equalize and the cold to disappear. An elastocaloric core operates in discrete compression strokes that can be matched to actual thermal demand. It does not need to run constantly, and a system without continuous mechanical operation is, by definition, substantially quieter than anything currently in your kitchen. Where this actually stands, the honest version of this story requires clarity about the gap between laboratory results and consumer products. There is no announced date on which you walk into an appliance store and purchase an elastocaloric refrigerator. What exists are prototypes and pre-commercial systems, impressive ones, that demonstrate the physics works at useful scale, but not products with manufacturing cost structures and warranty data that an appliance company could take to market. 3 specific obstacles remain. Nitinol is not an inexpensive material. The alloy must be produced under vacuum because titanium reacts with atmospheric oxygen, and the nickel-to-titanium ratio must be controlled with exceptional precision. A fraction of a % of deviation shifts the temperature at which the phase change occurs. These requirements mean specialty manufacturing rather than commodity production, and specialty manufacturing means costs that are currently not competitive with a compressor produced at global industrial scale. Replacing the compressor with compression does not eliminate the need for force. Something must drive the hydraulic system, and that driver now inherits the durability requirement that the nitinol component just shed. The mechanical driver becomes the component that needs to survive tens of millions of cycles, and appliance manufacturers require hard data on full service life survival before committing to production. Generating that data takes time that cannot be artificially compressed, because accelerating a fatigue test changes the conditions being measured. None of these obstacles are physics problems. They are engineering and manufacturing problems. They are the same category of obstacles that faced every technology currently operating at scale: computing, solar generation, lithium batteries at an equivalent stage in their development trajectories. The pattern is consistent. A thing works in a laboratory and appears economically impossible, and then manufacturing scale and materials science do what they have always done. Here is the symmetry worth holding. A man from Massachusetts invented the machine that made refrigeration a utility available to ordinary people. A Navy laboratory in Maryland accidentally produced the metal that makes a replacement physically conceivable. And a university team working a few miles from that same laboratory found the one direction of force that nobody had seriously tried for 50 years. The compressor in your refrigerator is not only in your kitchen. It is in your car, in the ceiling above your office, in the data centers running the applications on your phone, in the systems keeping battery packs in electric vehicles within their safe temperature range. Each of those applications has reasons to want what an elastocaloric system offers: no refrigerant gas, lower noise, solid-state operation, recyclable metal. The question for this community is one we genuinely want your answer on. If this technology scales across all of those applications, which one gets transformed first, and which of those compressor sounds, if any, would you actually miss? Leave your answer below. Your reasoning matters here, and it shapes what this community examines next. If there is another technology transition you think is moving faster than the public realizes, name it in the comments.